So hello everyone, and welcome to our 5th web seminar of the series of the Latin American webinars on physics. My name is Nicolás Bernal from the new ICTP SAFER, South American Institute for Fundamental Research in São Paulo, Brazil, and I will be your host today. So our speaker today is Julia Hoffman from the National Central University in Taiwan, who will talk about the new results from the AMS-02. She did her PhD in Warsaw in the National Center for Nuclear Research with the Delphi experiments at LEP. So after a postdoc in the Southern Methodist University in Dallas, she moved to the National Central University in Taiwan, where she's currently a postdoc working with the AMS experiments. Now she's based at CERN. So Julia's talk today is titled The AMS-02 Experiments, and we are glad to have her as our speaker today. So we remind you that you can be part of the discussion, writing questions and comments using the Google Plus Q&A system, and on Twitter via the hashtag LAWOP. This one. So Julia, it's a pleasure for us, and now we hand you over. So let me share your screen.
Thank you, Nicholas. Now I will share the screen. Hello, everybody. Let me just open my presentation. Oh, sorry. Sorry, I need to do this again. Okay, here we go.
Great. So, cheers.
Before I start, I would like to thank Professor Ting for his excellent presentation, which was given during AMS days here at CERN, and that was just 2 weeks ago. And the results that I'm presenting here are based on his presentation. AMS experiment. It is a particle detector which flies piggyback on ISS, on International Space Station. The detector itself is not very big if you look from the point of view of particle physics big experiments like ATLAS or CMS. It's just 3 by 4 by 5 meters. But in the space, it's the biggest detector of its kind. It weighs 7.5 metric tons, so it's fairly light, and the station flies roughly 400 kilometers above the ground. The detector has been taking data since May 2011, and it's fairly complicated unit with 650 processors and over 300,000 electronic channels. The AMS collaboration consists of about 43 institutions from 13 countries, plus CERN, and the latest addition is São Carlos Institute of Physics in Brazil with Professor Manuela Vecchi. And as you see in the map, the AMS collaboration is spread all over the world. The purpose of the experiment is to perform high precision, high statistics, and long period measurements of charged cosmic rays. And in this purpose, we are searching for cosmic antimatter, dark matter signatures. There are measurements of primary cosmic ray spectra, the abundances, ratios, isotopes, and composition, and also searching for new forms of matter and solar activity and more. The list of goals is fairly long. The detector is a precise multi-purpose spectrometer, and it consists of, let's say, 6 main parts. So first of all, let's go from the top. The first part is transition radiation detector, TRD, which gives us separation between electrons and protons and also identification of interactions. Then we have time of flight, TOF, which has 2 double layers, and it provides us with fast trigger, velocity measurement, and charge measurement. Then we have silicon tracker with 9 layers, and that gives us charge measurement and momentum measurement. Around the tracker, we have a permanent magnet, so we can distinguish between the positively and negatively charged particles. And on the bottom, we have ring imaging Cherenkov reach for velocity measurement and charge measurement. And last but not least, electromagnetic calorimeter for energy measurement and also separation between electrons and protons. So let's move to each detector with a little bit more detail. So transition radiation detector has 20 layers of fiber fleece and straw tubes, which are filled with xenon and CO2. And this detector gives us identification for electrons and protons based on transition radiation. And you can see here in the middle picture that the transition radiation lets us fairly well distinguish between electrons and protons, and based on that, we built probability, which is used later as estimator, and the power of separation you can see on the bottom right. So for time of flight, the time of flight consists of 4 scintillator planes. 2 are above the magnet, and we call this upper TOF, and 2 are below, and this is lower TOF. And the counters of neighboring planes are orthogonal. The TOF provides us with fast trigger, flight direction, and combined with the tracker also mass separation. Here on this colorful plot you can see the charge separation with TOF detector only, and we can distinguish charges up to zinc, which is, I think, fairly good separation. And on the top plots you can see the resolution for different charges, and it's also very good. The silicon tracker has 9 layers. They are spread throughout the detector. First layer on the very top, then second layer just under first TOF layer, and then we have 3 double layers, and at the very end, in between the reach and electromagnetic calorimeter, there is the last 9th layer. The overall detector material, the tracker material, it's very light, so it doesn't give too much interaction length for the particles to interact. And the inner tracker alignment is monitored with infrared lasers, and the outer tracker is continuously aligned with cosmic rays in a 2-minute window. So the alignment is very precise. The coordinate resolution is very good, of 10 micrometers. And here you can see the alignment accuracy for the 9 layers over 40 months. So you see that the alignment accuracy is very good. The ring imaging Cherenkov is a dual radiator detector. So most of it is aerogel with a hole for sodium fluoride. And to increase the ring acceptance, we have a conical mirror. And on the bottom, there is a detection matrix with over 10,000 photosensors. And it has a hole for electromagnetic calorimeter. So on the right-hand side, you can see what various nuclei would look like with the ridge detector. And the top pictures and the right bottom are from aerogel, and the left bottom is from sodium fluoride. So, and with this detector, We have very good identification combined with the tracker. We have good mass separation. And also this detector has very high resolution, much higher than time of flight. And at the end, electromagnetic calorimeter. It has 50,000 1-millimeter fibers, which are distributed in lead. It has 18 layers, and each layer has 72 cells, and this gives us high precision 3D measurement of the directions and energies of electrons and positrons to very high energies. And also, similarly to transition radiation detector, we have a classifier, an estimator that based on the 3D shower helps us separate electrons from protons. In the top plots, you can see the energy resolution and the angular resolution for this detector, which was obtained with the test beam here at CERN. The detector was launched on May 16 in 2011 in one of last Endeavour missions. We were very lucky that the detector is now on the space station. But how do we get the data? So the detector, you see, here it is in a square, and how do we transmit the data? So the detector transmits data through antennas which are on ISS to tethered satellites, and these satellites further transmit the data to White Sands in New Mexico, and from there the data gets directly to CERN, to our control room. But in case that we unexpectedly lose connection with the satellite, it happens sometimes, we have a backup AMS laptop which is placed in the astronaut living areas. You can see a little picture of astronaut on ISS with our laptop. So the data is transmitted simultaneously to the satellite and to the laptop, and we can retrieve missing data later. And because there is no chance of detector upgrade, technical stop, as you can think with LHC, our detector control is 24 hours a day, 7 days a week, and 365 days a year. So this is non-stop operation. In 4 years of operation on ISS, AMS has collected over 60 billion cosmic rays. So this is very impressive in my opinion. And because we do not have a sister detector to collect similar data, to ensure the quality of the analysis, each analysis is performed by at least 2 independent teams from various institutions, and then the results are compared for consistency, and then they are being processed for publication. So I would like to start with the newest result, with the newest publication, which has just been published, and this is precision measurement on the proton flux in primary cosmic rays, from rigidity of 1 gigavolt to 1.8 teravolt. And so the proton flux is defined as a number of events in effective acceptance, trigger efficiency, and collection time, and also in a given rigidity bin. And because we are proud of our very high statistics, and the statistical error is so small that it's important for us to do extensive study on systematic effects. And these include trigger efficiency, acceptance and event selection, background contamination, geomagnetic cutoff, unfolding, rigidity resolution, or absolute rigidity scale. And you can see in this table on the last column that the error is fairly small. And here is the AMS proton flux as a function of rigidity. And if you want to compare it to other experiments, you can recalculate it into kinetic energy, and this is what it looks like. The AMS results is red dots. And you can see that, yes, indeed, the statistics is really high and the measurement is very precise. So now you could show this result in various ways. So one of them is the proton flux with a fit of power law. And from here you see that you cannot really fit it with one power law, you have to fit it with two. And in the top corner you see the function that was fit into the data. And R0 is characteristic transition rigidity and S is smoothness. So the solid curve is the fit with the two power laws, and the dashed curve uses the same fit, but the delta gamma, the second power law, is set to 0. And you could also present it in a way of model-independent measurement of spectral index. And this is the function that you're using to make this this plot. Okay, so let's move to the exciting part that many of us think and maybe wait, the dark matter part. Dark matter. Okay, we know it exists. We know it makes roughly 90% of matter in the universe. But we don't know what it is. We have some theories and some candidates, and we would like to confirm whether this is the candidate is good or not. So, you would expect in collisions of ordinary cosmic rays to produce secondary antimatter like positrons or antiprotons. And you would expect certain behavior in fluxes or ratios. So in these plots that you see on this page, you see in green the expected what would a ratio on the left for positrons and on the right for antiprotons, what it would look like if we had only collisions of ordinary cosmic rays. And but then collisions of dark matter would produce additional positrons and additional antiprotons. And if that was the case, you would see here in blue and in purple on these plots, you would see an excess on top of the regular collisions. So let's look at the AMS data. To identify the signal coming from dark matter, we need measurement of electrons and positrons and antiprotons, then precise knowledge of cosmic ray fluxes like protons, helium, carbon, and so on, and propagation and acceleration parameters, which you can get from fluxes or ratios of other elements. So now, the positron fraction. This is the result from AMS, which was published 2 years ago. And you can see that the positron fraction is not going down, but at some point it starts going up. And then it flattens. And if you were trying to translate this positron fraction into whether we do see dark matter or we don't see dark matter, it would look roughly like this. On the left-hand side, you see the current status with current data. And the blue line would be the astrophysical known sources, for example, pulsars. and the brown line would be a dark matter candidate, neutralino, of a mass of 700 GeV. And then if you look at the data, you cannot really say, because it does not confirm any discovery, it does not deny it. But if we wait long enough, say 10 years from now, with very high statistics, we could, at this point, we could say whether it's pulsars or it's dark matter. But also the positron fraction, it's not the only thing that we need to look at. Excuse me. So if we look, let's look at the electron and positron fluxes. So the flux is defined the same way as for protons. So we have a number of electrons or positrons in the effective acceptance, the trigger efficiency, and the exposure time, and also in the bin of energy. So now, this is the electron flux as a function of energy as compared to other experiments. And this is positron flux, also as a function of energy and compared with other experiments. So if we look at two these fluxes together, you can see that both of them are different in the magnitude and energy dependence. Both spectra cannot be described by single power laws, and the spectral indices for electrons and positrons are different, and they change behavior at around 30 GeV. And you can see also that the positron flux is harder. The rise in the positron fraction is due to an excess of positrons and not loss of the electrons. So this is about electrons and positrons. And the next result I want to show you is antiproton to proton ratio. So this is the newest result. It is still preliminary, and it hasn't been published yet. We are still ironing out details of the analysis, but this is preliminary result. And also, you can look at this comparing to other experiments, like here with Pamela and Bess. And you can have a look at our data with the secondary production model, and you see that there is some excess. Now, it's hard to comment on that. We need some comprehensive model to work with the data. So now if we look at the nuclei and at the measurement of nuclei with AMS, they're usually done with charge measurements. The identification is done by charge, and we have several systems to give us this charge measurement, and also to see if there are interactions that cause a given element to appear. And for now, you can see this is our ability to distinguish various elements by the tracker charge and by the time of flight charge. So now, if we move to various nuclei fluxes, here you have helium flux compared with other experiments, and similarly to protons, you could show this flux with a fit to 2 power law. You need 2 power laws to make a fit to do this data. And the turning point, the change of slope, it is at similar, pretty much the same energy as rigidity as for protons. And if you make proton to helium flux ratio, this you can describe with a single power law above 25 gigavolts. So you can say that their behavior is similar. Now, with the lithium flux, this is again the current status. It hasn't been published. It's just preliminary, and you can see that this is pretty much the first results after 40 years from the last results, and you can see the precision. So this still amazes me, the precision of this data. I know I'm bragging about the experiment, but you see why. And again, the lithium flux again can be presented with 2-power law fit. And again, the slope changes at about the same rigidity as for protons and helium. And also one of last results, which is boron to carbon ratio, which is important for the propagation of cosmic rays. This is presented as a function of rigidity with 40 months of data, 7 million carbons, and 2 million borons analyzed. And this data can be shown in kinetic energy, and also it is shown with other experiment results. And the blue dashed line is fit to positron fraction with a secondary production model. So you see that the model tends to flatten at higher energies. The ratio tends to be going down. This is yet another thing that we need to explain with good models. And now I would like to summarize. In the past 100 years, the measurements of cosmic rays by balloons and satellites yielded uncertainty of about 30%. The AMS experiment provides cosmic ray information with uncertainty of 1%. And you saw yourself, the latest measurements provide precise and unexpected information. And it will require a comprehensive model to make sure to find out if their origin is from dark matter, astrophysical sources, acceleration mechanism, or a combination of those. Thank you very much. Are there questions?
Okay, I have a question here from Ifik in Valencia. So, do you know if there is, maybe if you can comment more about this spectral break, why is common to many nuclei cosmic ray species?
This I don't know.
Explanation or it's just a mystery?
If I remember well, the comments on the fluxes, that was that we really need a good model to explain this. And actually, we are in collaboration with some theorists. One of them is Igor Moskalenko, who's one of authors of GalProp. He's amazed by the results, and he requests from us more ratios, more data to get better models. So maybe this question would be because right now I'm waiting for my colleague to join, and when it comes to the fluxes behavior, he probably will be able to answer in more detail to that question. He will join in a minute, and we can discuss about this further.
Okay, thank you. Another question, just to, but this is about, I mean, because last week AMS released the new result, another new result. When do we expect a new update of the data? I mean, because now you have a lot of the statistics. I don't know how much we have to wait to get improved in the fluxes and in the statistics in the high energy part of the spectrum.
Okay, so for now, there will be just current data, like around 40 months, and we have a lot of other results to show. So it's the helium flux, which is in preparation. There is anti-proton ratio, which is in preparation. There are nuclei fluxes, which are in preparation. So first, we need to work on these, and actually to update the statistics, we would have to wait some more time, but how much, I don't know. And right now, my colleague have joined, Professor Sadakazu Faino, please come in. So there was a question about if we can explain the behavior that all the fluxes start turning the slope at the same place.
Yeah.
You can comment on that.
No, this is what we observe, so we expect theorists to find a good theory to explain it. This is our measurement, so we don't know. Yeah, we just measure it.
Sorry, yeah, my question was if you can comment a little bit more about this spectral break and why it's common to so many, I mean, from from protons, helium, lithium, and all in the same range, in the teravolts of rigidity. That was the question that I did in the beginning.
So let me repeat the answer. So like I said before, and also Sadakazu repeated, we don't know why. So we need we observe it, and we need a good theory model to tell us why. Does that answer your question?
Yeah, that's good. So we have, I guess, we have another question from Timur. I mean, now I'm kind of helping because the host has some problem with his micro, so he is not going to be able to moderate the session. But anyway, if Timur can ask to unmute. It seems that also Timur has problem with his micro. So anyway, but there is a question from the Q&A that I can read it. It's like in the slide 31st, could you provide details on how was the uncertainty region, the brown area, calculated? In the slide 31st of your presentation.
On slide 31st, yes. So what is the uncertainty on the data or on the model?
On the brown area.
So this brown area, it is the range of the model. This is together with the uncertainty. So I believe that you could, I don't know, put a line through the center of this area to get more or less the tendency, and the area is the uncertainty.
Yeah, but this is taken from a particular paper. If you read the press release of AMS, it is not written here, but if you read the press release, it is written, this is Donat et al. In 2008 or 9, I don't know, some old paper. We show this because just an example, because there are lots of predictions. So we took just one model for the presentation. Of course, this is you may say this can generate some bias because we are observing the excess from antiproton, but our message is there are still large uncertainties on the secondary production, But after our data of proton, helium, and nuclei data, we expect theorists to improve the secondary prediction. So this is our message.
Okay, thank you. It seems that now Timur can make the question that he was wanting to ask.
Can you hear me now?
Yes, we can.
Great. So at the beginning of your presentation, you mentioned that AMS will be able to measure isotopes of different elements. So I'm thinking, of course, of beryllium or aluminium. But when you show the mass reconstruction, you never show these isotopes. So what should we expect?
Well, the composition is probably not on very high, at this moment, not very high on the list of things that we are doing. So we do not have now results to present. But there are people working on it, and so, for example, helium composition or lithium composition, these things are in the works. But right now, there are no results that I can show you.
No results, I understand, but sensitivity or anything, you don't have that yet?
No, I don't have that yet.
Okay, thank you. And so, so you said that the proton anti-proton to proton ratio you showed was only preliminary, but yet you called for a press conference for it. So how are we supposed to understand that? Should we use this data to work on it, or should we wait, or what's the meaning of that?
Yeah, this is a good question. But if you can answer me. If you look on the archive, there are already quite a few papers on this data. So we don't prevent people to work on this, but we just say they are not final data, just a status report. So maybe you can wait for the final data if you want. But it doesn't prevent you to work on now.
Yeah, also, I believe that the data you see will not change drastically.
But the proton flux has changed quite a lot since the ICRC, so are you really sure that the anti-proton will not change this time?
Well, many things have been improved since ICRC with respect to the proton flux, and with these improvements, we present the proton results.
Okay, and so you showed the proton flux that is quite different from the Pamela one, and your helium flux is quite different from the cream one. So I mean, there are different experiments and so on, but do you have any feeling of what is going on? Do you think that I mean, what could be the explanation of such discrepancy?
Do you have a comment on that?
Yeah, we are responsible to only our data. We are not qualified to discuss about other people. But the important thing is we make sure our data are correct.
So, like I mentioned before, to ensure that that we are not biased with our analysis, usually the analysis is done with at least 2 independent teams, and then the results are compared for consistency. So separate groups have concluded, have come to a conclusion that this is the flux. And this is how we see the events.
Okay, thank you. No, I understand that, but I remember that, for instance, in gamma rays, when they long time ago they saw an excess, and then Fermi did not see it, then they decided to work together to find out if there was a problem with the previous experiment. Do you consider maybe discussing with the Pamela people to try to find out if there is a problem in their experiment or not?
This I personally don't know.
No, we don't think so.
All right, thank you very much.
Okay, we have other questions from the people doing they are watching the streaming. So we have a question from Mauricio Bustamante from Ohio University, Ohio State, that he's saying, after AMS presented the new anti-proton result, there was a paper, an Albert, that claimed that the uncertainties in the secondary anti-proton production is still compatible with the anti-proton-proton ratio. This would disfavor the dark matter interpretation. Does AMS have a comment on that?
I'm not sure I've seen this paper, but like Sadakazu mentioned earlier, there are models on secondary production that could have high uncertainty. So to actually explain the match or the lack of it with the data, one would have to have a fairly precise model.
Okay, I guess this answered a little bit the question. Another question that maybe Joel can use his microphone, or I don't know if, Joel, can you?
Let's see, can you hear me?
Yes, we can hear you.
Okay, great. No, so this is related to the previous question, because the Piero jet experiment is suggesting that at high energies, the composition of cosmic rays is mostly from heavy particles like iron, right? So my question is if that would have any consequence on your predictions for the positron, the anti-proton fluxes. I mean, I really don't know what goes into the original prediction for these fluxes. So I want to know if this would have any effect.
Well, that would require proper modeling on the heavy ions propagation, I believe, and the behavior. So like I mentioned, we are working with theorists and providing as much data as we can to help the models. So at this moment, I don't have an answer to that question.
Okay, thank you very much.
Yeah, maybe we have more questions. I don't know, people that is attending to the Hangout session. I don't know if Herman has a question. Okay, in the Q&A, we don't have any more questions, so I guess if this is all, we thank you very much, both of you, to participate in this Hangout, and all the people that are following and will see the offline version will be very thankful for all the explanations. So I guess, applause.
Thank you.
Thank you. Thank you very much. And next webinar is going to be about the Fermi results and this combined analysis with the dark energy survey, just for if you want to join us. Anyway, thank you very much.
Thank you. Bye-bye.
Bye-bye.